Our homework from last night was page 538. Lots of questions to go over this morning, starting with number 2. Number 2, more just a qualitative question. Sometimes a question like this, the problem with it is that we're just not even sure exactly what we're being asked sometimes with a question like number 2. It says, describe how the inverse square law first proposed by Newton for gravitational forces was applied to the electrostatic forces by Coulomb. Well, what is the inverse square law, first of all? We've learned 2 inverse square laws. The first one was Newton's law of universal gravitation that we learned in physics 20 that said basically F is equal to G m1 m2 over r squared. The second one that we've just learned here in the last week or so for Coulomb's law, F is equal to K q1 q2 over r squared. So an inverse square law basically says that F is equal to something times 1 over r squared. It's related to the inverse of the square of the distance. So how does Coulomb apply his law, or apply the inverse square law first proposed by Newton for gravitation to electrostatic forces? Well, my interpretation of this question, at least, is simply to say that, look, he recognized that charges are analogous to mass. Okay, when we're talking about electricity, there's a force between charges, just as there's a force between 2 masses, a gravitational force between 2 masses. That force is related, directly related to the product of the charges, just like gravitational force is directly related to the product of the masses. And it's inversely related to the square of the distance, just like gravity is inversely related to the square of the distance. If there's this invisible force that acts between 2 masses a certain distance apart, then why wouldn't the same relationship apply between 2 charges a certain distance apart? Okay, that was his law between 2-point charges. Okay, same law, effectively the same law as applies between 2-point masses. And when he does his experiment, torsion balance experiment, he finds, sure enough, that law or that relationship does apply. The same relationship as he hypothesized that existed between 2 charges. The same relationship that we already knew applied between 2 masses. Is that kind of okay? 3B. Let's just do all in number 3 here. It says, what's the SI unit for electric charge? SI just means, it's French, right? System International. My accent is horrible, but it basically means the metric system. What's the metric unit for electric charge? Coulomb, right. It's the Coulomb, C. Compare the charge on an electron to that produced by rubbing an ebonite rod with fur. Now, honestly, you can't quantitatively compare these two, because honestly, you have no idea how much charge is produced by rubbing ebonite rod with fur, this kind of plasticky, rubbery rod against fur. You have no idea how much charge is produced, but you do know that it's going to be a lot more than the charge of an electron, right? Okay. When you rub it, you rub 2 things together like that, you bring something nearby hair, it'll make your hair stand on end. Well, an electron is not going to make your hair stand on end. So it's got to be a lot more charge. You've got to have a lot more charge, a lot more electrons transferred between the fur and the ebonite than one single electron. So can't compare it numerically. All we can do is kind of anecdotally say, look, it's a lot more when you rub 2 things together than it is when you just have a single electron. 4. Oh, this is a good question. We talked about that with the torsion balance experiment, right? Coulomb could not measure the amount of charge on his spheres. He could not do that. But he could vary the amount of charge on each sphere. So ultimately what he did, right, was plotted a graph of F versus Q1, graph of F versus Q2, so on. In order to do that, he needed to manipulate the value of Q1. He needed to manipulate the value of Q2. So he needed to change the values of these charges, but he didn't know what the charge was. He didn't know the exact value. He couldn't measure the value of the charge on the sphere. So what did he do? Compared relative values, right? Remember we talked about charge 1, let's say, has a charge of Q. We would just call it Q. We touch it against something that's neutral. What does it become? Q and 0 become half Q, right? Half Q and half Q. So we started off with Q, and then in the next trial for the experiment, we've got a half Q. Well, let's touch it against something that's neutral again. It becomes a quarter Q and a quarter Q. We keep doing something like that, and we end up getting all these different trials with different values of charge. Again, we don't know what it is in coulombs, but we do know what it is compared to what it was at the beginning. And that's all we need to know. We're not trying to find a number with this experiment. All we're trying to do is find a relationship. And all we have to know to find a relationship is, hey, what's the charge basically compared to what it was when we started the experiment? Okay, so we manipulate the charge without really knowing what its value is. You know what? We could create our own units here in a sense. Okay, we could create our own units. We could say that whatever this is, whatever value of coulombs this is equal to one, let's create a new unit for charge, 1 night. That's our unit of a charge now. Okay, that's 1 night. Well, then this is going to be 0.5 nights, and 0.25 nights, and 0.125 nights, right? And so on and so on and so on. So we're just essentially using a different unit when we do that, making up our own unit when we do that. Next question, 6. Why is it difficult to attain a large charge of 100 coulombs in a small object? There's a good question too. A little bit of a thinking question. There's some good ones in here actually, not just those regurgitation, here's what I told you in class, repeat it. This is what you got to think about. Why do you think it would be difficult to get a large charge, 100 coulombs? I mean, that's a lot of charge, right? 1 coulomb is a lot of charge. 100 coulombs is, for those of you who are math challenged, 100 times that, which is a whole lot of charge. Rucker, why would it be so difficult to get that much charge on a small object? No, you could probably get physically enough atoms with enough electrons. Yeah, it's a good idea actually, Rucker, but you probably could physically get enough atoms to do that. It's less a matter of that and more a matter of something else. Yep. Okay, the surface area is smaller. Yes, you're getting there. And it's easier to transfer because the surface area is smaller. Why would that be? Oh, okay, so there's so much charge in such a small area, it's difficult to kind of hold it. Okay, it's kind of like, I think I used this analogy one day before. If I'm holding my arms out like this, and you put a basketball in my arms, I'm able to hold that. Another one, I'm able to hold it. Another one, I'm able to hold it. But at some point, you keep putting basketballs in my arms here. At some point, they're going to discharge. They're going to start falling to the ground because I can't hold it anymore, right? Okay. Okay. Good. Okay. You're right. Okay, you're absolutely right. They can't hold it at some point because they're so small and small surface areas can't hold it. But why can't they hold it? Okay, when I'm holding the basketballs, why can't I hold it? Because eventually gravity is too much of an issue, right? Why can't they hold it? Why can't small objects hold charge? Well, because you get too many electrons. Okay, 2 electrons repel each other. But if you get 3 electrons, 4 electrons, 5 electrons, they repel each other even more. And at some point, the force of repulsion is too big that a small object can't hold it. You get a big object, it can hold more charge. Why? There's more room. The charges are further apart because there's more room, and the force of repulsion isn't quite as big then, right? But you get a small object, they have to be really close together. And if R is really, really small, then the force is really, really big, and they can't hold each other. Okay, does that make sense, guys? All right, number 6b says, during the rubbing process, an object acquires this much charge. How many electrons did the object gain? You know this, right? We did a question like this on the first day, I believe it was, of this unit. Remember what we said when we're trying to find a number of something? Forget about this question right now. You're trying to find any number, a number of something. A number of electrons, a number of photons, which you haven't even heard of yet. Okay, a number of alpha particles, a number of anything, a number of oranges in the bag. That was our analogy, right? What do? What do you always do when you're trying to find a number of something in physics 30? Good. Take the total and divide it by the amount of 1. Here it's going to be the total charge, 5.0 times 10 to the minus 9 coulombs, divided by the charge of 1 electron. Total charge divided by the charge of 1. And when we do that math, We get 3.125 times 10 to the 10 electrons. Total charge divided by the charge of one electron. Total mass divided by the mass of one something. Total energy divided by the energy of one something. In this case, since we've got charge, let's use charge. Okay? If we've got a question, honestly, I would anticipate in the context of charge, but if you had a question where you had the total mass of electrons, you wouldn't say charge over charge, you'd say the total mass divided by 9.11 times 10 to the minus 31, the mass of one electron. Usually for electrons, it's going to be charge. But for other things, it could be mass, energy, whatever. All right, number 9. A helium nucleus has a positive charge of the magnitude twice that of the negative charge on the electron. So if you're taking chemistry, you'll be familiar with how this works, right? In a helium nucleus, there is going to be 2 protons, always, always. If there's not 2 protons, it isn't helium, right? If there's only 1 proton, it's hydrogen. If there's 3 protons, I think it's lithium, isn't it? You gotta have 2 protons if it's going to be helium. Otherwise, it isn't helium. Now, normally in helium, you're going to have 2 neutrons as well, but you can have a different number of neutrons in helium. You could have 1, you could have 3, depending upon the isotope of helium. Okay, for protons, got to be 2. Neutrons could be a few different combinations of them. Electrons, well, normally there's going to be 2 electrons if you get a helium atom, 2 electrons orbiting around as well. But that's not the question at hand. The question at hand says the helium nucleus, this object in the middle, has a charge of twice the charge of a single electron that orbits around. And that makes sense, right? Because we get 2 protons in the nucleus, 1 electron. So this is going to be 3.2 times 10 to the minus 19. This is going to be 1.6 times 10 to the minus 19. Here's the question. Is the electrostatic force of attraction, and it is attraction, right? Positive attracts negative, in a helium atom equal to the force acting on the nucleus? So we know that the electron pulls on the nucleus. We know that the nucleus pulls on the electron. Are the forces equal? Or because the charge on the nucleus is bigger, is one of those 2 forces bigger than the other? Rucker? Good. Good. They're going to be the same, but they're going to be in opposite directions. Now, a lot of people are going to say, oh, look, the charge of the nucleus is twice as much, therefore the force is going to be twice as much. No, it's not. F is equal to K, Q1, Q2 over R squared. That force acts between Q1 and Q2. Doesn't matter which one's bigger. The force on Q1 is the same value, but as Rucker said, opposite direction to the force on Q2. That's Newton's 3rd law. Remember that from Physics 20? Object A applies a force on object B. Object B applies an equal and opposite force on object A. Who remembers that? Sometimes we forget which law is which, right? You know, forget, oh, was that the 2nd law? Was that the 3rd law? Whatever. But somewhere in our mind, we all remember that law, right? Every action, there's an equal and opposite reaction. Okay? Whether we remember which law it was or not, we remember that it's a law. Okay, finally, number 10. Number 10 says the electrical forces are so strong that the combined electrostatic forces of attraction acting on all the negative electrons and the positive protons in your body could crush you to the thickness thinner than a piece of paper. Why don't you compress? Why don't you compress? Force of attraction, listen carefully, the force of attraction is strong enough to compress you to the thickness of a piece of paper. Brad, why don't we compress that? Because there's a force of repulsion as well. Where's the repulsive forces come from? Yeah, each electron from each other, but bigger than that is, yeah, it's the nuclei, right? The nuclei repelling each other, right? We're not going to crush to the thickness of the paper because those nuclei can't get close enough to each other, right? The closer they get, the bigger the force of repulsion becomes. Okay, so at some point it becomes so big that it's just not going to compress anymore. At some point, you reach this point of equilibrium, right, of balance, where you got attractive forces, you got repulsive forces. Okay, this is where we are. Was there a hand up over here? No? You're good, though? Okay. Is that good? All right, let's spend just a couple minutes reviewing yesterday's work here now. We talked yesterday about electric fields, fields in general, as being lines of influence that surround something. Electric fields, lines of influence that surround objects with charge, versus gravitational fields, lines of influence that surround objects with mass. We talk about this concept of fields in contrast to the concept of force. The difference between them is important, right? We've got a force of gravity acting between you and the Earth right now. But if you walk away, that force of gravity at that spot where you were is not there anymore. But the Earth and its influence is still there. We have to have some way of describing the influence of the Earth, even when there's nothing there to be influenced. That's the idea of fields. The influence of the Earth, even when there's nothing to be influenced. Okay, gravitational field. Well, the same deal kind of applies to charge, right? You got a charge here that causes a field. You got something experiencing that field out here. If you take that away, though, the influence, the charge that's causing it is still causing the same thing. There's just nothing there to be influenced anymore. So there was a force when there was something there to cause it and something there to experience it. But when there's only something to cause it, we still have that something, so we're going to call it a field. That's an electric field, when we have something to cause the influence, regardless of whether or not there's something there to experience the influence. We talked about electric fields and gravity fields both as being vector fields because they have a direction, versus, say, a scalar field that has no direction, light field, heat field, and so on. The difference between a force and a field, right? Need a producer to have a field. We need a producer and an experiencer to have a force, right? In order to have a push or a pull, which is a force, you need something to be pushed or pulled, okay? Let's say Aiden is our producer here, okay? He's pushing like this, okay? That's there, right? He's pushing no matter what. But go ahead and push, Aiden. Push, just start pushing, push. You can push better than that. Oh, but all of a sudden, when I get in his way, I'm an experiencer. I feel that push, right? Now there's a force. Okay, when he was just pushing, you can't have a push without having something to be pushed, right? But Aiden's still there. So what caused it is still there. The potential to influence is still there. You're just not experiencing a push until there's something there to feel that push. And finally, we talked about the electric field direction. It's the way that a positive particle moves when placed in the field. It goes away from the positive toward the negative. Let's say, let's draw one field line right here. There's my electric field. Okay, I'm going to ask you a few questions about this one electric field. First of all, actually, no, let's do this. Let's put a negative particle in that field. Tell me which way that negative particle is going to be forced. There's going to be a force on that particle. Which way is it going to be forced? It's going to go to the right. It's going to go opposite to the direction of the field. That's because the positive particle, the way we define the direction of the field is the way the positive particle moves when placed in the field. Tell you, which way is this going to go, the positive? Good, in the direction of the field. Here's another question. There's my producer. What kind of producer is that? Is it a positive producer? Is that a negative producer, Lewis? It's a negative producer. How do you know that? Good. Field goes toward the producer, it's got to be a negative producer. Is that the only possible explanation for the creation of that field? Or is there anything else? Is there something else that could have caused that field? What if I took this away? And what if I put this field or this producer over here? Is that a possibility? Rucker, what would that have to be in order to cause that field? That would have to be a positive charge, right? Is this a possibility? Would you have a positive and a negative? Yes. Okay, the first two questions that I asked you, which way does the positive go, which way does the negative go, it doesn't matter what caused it. There was something to cause it. There was a producer or more than one producer there. We didn't know what it was. We didn't really care what it was because we know that a positive experiences a force with the field, a negative experiences a force opposite to the field, regardless of what caused it. But there was something there to cause it. We just didn't know what it was. All right. Finally, we looked at three equations that were similar to our gravity equations. Our first one was for electric force. F is equal to K Q1 Q2 over R squared. Hey, that's not new. We've been looking at that for over a week now. The second one was for gravitational field or electric field. So was the third one. So what's the difference between the second one and the third one? Yeah. Good. When you have information about what causes the field, whether it's gravity or electricity, we're going to use the second equation. When you have information about what experiences the field, we're going to use the third equation, and that's the experiencer equation. Now, one final thing before we take a look at those questions that we were working on yesterday. I mentioned to you yesterday that the symbol for electric field is real similar to the symbol for something else. What was it? What was that other thing? Energy. Right? What's the difference between the electric field and energy? Not conceptually, but symbol-wise. Okay. Energy is a scalar, electric field's a vector. So this would be energy. This would be electric field. Sometimes we see, oops, that's not really an E, I guess, is it? That's the electric field. Sometimes we see those absolute value signs around it. Sometimes we don't. We're not going to lose sleep over that. But we are going to really focus on putting that vector sign over it. Don't forget that. You will at some point. I promised you this yesterday, and I'll stand by this. At some point this year, if you don't put the vector sign over the electric field, you will get electric field and energy mixed up, and you will make a mistake on a question. I promise you, every one of you will do that if you don't consistently put that vector sign over it. If you do consistently put the vector sign over it, you might still make that mistake. But it cuts your odds down dramatically if you distinguish between the two of them in that way. All right. We were working on some questions yesterday from 548 and also from page 549. Any issues with either of those sets of questions, 548 or 549? Good? Anybody? It's all good? All right. Excellent. Well, then let's do one more question. This is the only question that I want to do with you today, besides what we've already done checking homework. One example, that's it. 11.3 on page 550. It says two positively charged spheres, A and B, 1.5 times 10 to the minus 6 coulombs, 2.0 times 10 to the minus 6 coulombs. Hey, this could have been expressed, and it often will be on a test, not as 2.00 times 10 to the minus 6, but as 2.00 microcoulombs. We've got to be able to do that conversion, right? Check your data sheet. You would see that this is 10 to the minus 6, so it is 2.00 times 10 to the minus 6. They give it to us in this question, but they don't always. They don't always do that. Okay, a lot of the time they leave it in microcoulombs, and we've got to do the conversion for ourselves. So they're this far apart. We want to find the net electric field at a point midway between the centers of the two spheres. All right, any ideas? Any ideas? Good, Rucker. I will use the producer equation because I have two producers here. I'm trying to find the field strength at a point P where there is nothing to experience it, at least nothing that we know of to experience it. If there is something there, we don't know anything about it. There's two producers. We've got to use the producer equation. But be careful, because when we use the producer equation, we have to use it separately for each of the objects. Before we use that producer equation, though, to find the field, what are we going to do? Something has to come first. Okay, let's split the radius in half. Not really a radius because it's not a circle here, but the distance in half. Sure, so that's going to be, what do we got there? 1.65 times 10 to the minus 2. And then the other one is also going to be 1.65 times 10 to the minus 2. Okay, so Rucker says use the producer equation. Rucker, I should have written that down when you said that, because whenever you have a thought that seems valid, it's a good idea to write it down somewhere, even if it's not what we're going to do first, right? Because a lot of times what happens is, we get these questions that are so long and there's so much work to them that we think of these things, but by the time we actually get to that step, we forgot that step. So as you think of something, write it down. What else? If we've got two producers in two fields caused by the two producers, then we're going to have to combine them, right? But how do we combine them? Add them together? What if they're not in the same direction? Well, then maybe we subtract or add a negative, right? Well, how do we know that they're not in the same direction? Or how do we know that they are in the same direction? Okay, let's draw a little bit more on this diagram. Okay, let's do that. Charge number 1 is a positive. Here's a positive producer. Charge number 1 is a positive. And we're looking to the field to the right of charge number 1. Take a look at to the right of a positive producer. Which way does the field point? To the right side of a positive producer. This is the right side of a positive producer. Which way does the field point, Aiden? To the right. So we're going to say the field caused by number 1 is to the right. Now, point P is to the left of producer number 2. To the left of a positive producer, which way does the field point? To the left. So let's say E2 is to the left. Does that make sense? This is not a free body diagram, because free body diagrams show forces, but it's kind of like it, right? It's kind of like drawing the forces in those, and when you have those 3 charges. Okay, you know where to go now. Rucker said a few minutes ago, use the producer equation. Okay, so let's do that twice. Let's say E1 is equal to KQ1 over R squared. Don't forget to square that. This side of the room here. These 3 rows. Calculate E1 for me, please. E2, which you guys on this side of the room are going to calculate, KQ2 over R squared. K is the same. Q2 is 2 times 10 to the minus 6, and the distance is the same as well. Does anybody else get that? 4.95 times 10 to the 7? Good. Thank you, Georgia. That would be newtons per coulomb, right? Okay, and what about the other one, this side of the room? Yep. 6.60 times 10 to the 8. Anybody else get that? Yes? Okay, so now let's add them up. I'm sorry? Yeah, that makes a little bit more sense, actually, 10 to the 7. Just check that, because I'm just looking at this one. Okay, the charges are real similar here. Okay, this one should be 1/3 more than this one, and we had it more than 10 times more than that one, right? 10 to the 7. I'm sorry? Okay, that'll do it. Yeah. So now let's combine these, right? Now let's say the net field is equal to field 1 plus field 2, which is field 1 is 4.95 times 10 to the 7 plus negative 6.60 times 10 to the 7. We do the math, we should get, what is that going to be? 1 point, it's going to be negative, isn't it? Which tells us, of course, that we have a net field to the left, right? You guys okay with that? You guys starting to notice that as we do things that, look, we're doing new concepts like, you know, like electric force and like electric field, but a lot of it still kind of ties in with stuff that we've done, right? With electric forces, you know, it was free body diagrams, combined forces, just like we did in physics 20. And then when 2 dimensions, it was vector diagrams, just like it was in physics 20, with forces, electric forces tossed in there. This, hey, electric fields was new to us yesterday. We haven't done a question like this before either, but you notice how it's, even though it's a different concept, it's still kind of the same as dealing with the electric forces there, adding up the forces, except this time we're adding up fields. That's where we want to be, right? We want to see those connections between fields and forces, and even between electric forces and, you know, the elevator problems that we did last year in physics 20, where the net force is the sum of the forces. All right, let's take a look at these 2 questions for now and see what you can do with those. All right, just had a question about question number 1. Lots of us are getting the wrong answer because as we refer back to 11.9, lots of us are saying, oh, okay, we're trying to find the field strength right here, 2.10 times 10 to the negative 2 meters to the left of that. And you're forgetting about this. But 11.9 has the rest of it in it as well. So what you got to do here in question number 1 there is say, look, the field caused by number 1 is away from it. Right? Here's a positive producer. The field to the left of a positive producer points to the left. But the field caused by number 2 is a positive charge as well. So the field caused by number 2 is also to the left. It's away from that positive producer. To the left of a positive producer, it points to the left. So you get 2 fields that point to the left here. You got to calculate both of those. E1, KQ over this distance squared. E2 is KQ over, what distance would we use for KQ? Or for E2? This distance plus this distance? Right, the distance from charge number 2 or charge B to that point. Does that make sense? In addition to those questions on page 550 for homework, I'd like you to do the following questions on page 553. So we got a couple questions on 550, and then we got 9 questions here on 553.